Okay. Right. So again, so what we need to see is actually the shell energy balance is actually similar with the momentum energy balance. Yeah, so you have to see the analog between momentum energy balance, momentum balance, and also the shell energy balance. Okay, if you understand the momentum balance really well, then you should be also understand about the shell energy balance. Right, so here we have the rate energy transport minus energy convective transport, and then with the energy in by molecular, and then the work done on the system minus by the system, and then the rate forces, okay, and then plus the rate of energy production. Okay, and then so here we see all the components. Pak Anggit has explained that one last week. Okay, and then so if you want to watch or if you want to maybe consider the analog between momentum transport and energy transport. Okay, so your for the molecular energy is the same, but for the molecular energy for the molecular transport, if you in momentum transport you use the Newton's law, which is tau, for example, xy equal to minus mu d vy to dx, for example. Okay, but in energy transport we use conduction, so and it's called Fourier's law. Fourier's law, yeah, which is q would be equal to minus k d t over dx, for example. Yeah, so if you think about it, this also driving force. This also driving force. Yes. The higher you have the driving force, for example, the driving force of the velocity within the different distance, okay, and also the driving force of the temperature with different distance, then you will have a higher driving force. And the second one, this one is actually a quantity which is called for about the resistance. Okay, this also resistance. If you have a higher viscosity, then you also have higher shear stress. If you have higher thermal conductivity here, then you will have also have a higher Q or the heat flux. Okay, so this one is and this one is called momentum flux, and this one is called heat flux. Okay, so it's quite similar between the momentum transport and also energy transport. And later on, when you see the next module about the mass transport, they're also similar with analog with momentum transport and also with energy transport. Okay, right. Okay, and then this one, the molecular work, and then external forces and energy production. So we'll see in a minute. And then the typical boundary condition, this is also similar with the momentum flux. Okay, so sometimes the temperature may be specified at some surveys. For example, if we said, for example, at R equal to R, you know the temperature is defined, for example. Yeah, this is just example. Okay, or sometimes it's typical boundary condition that you're gonna see in some examples would be a heat flux. Okay, and heat flux is called Q. Okay, heat flux, what we call it heat flux, is actually the rate of the heat divided by the area. Okay, so it's actually the rate of the heat, or Q, divided by the area. Okay, similar with momentum flux. If momentum flux, for example, is equal to the shear force at that area, yeah, at that area, for example. Okay, so here, so usually the heat flux normal to the surface may be given. This equivalent to the specific normal component of the temperature gradient. Okay, and then so this is a typical boundary condition number 1. This is typical boundary condition number 2. And then number 3, at the interface, the continuity of temperature and heat flux are normal to the interface as required. So it's just about the continuity, and also the heat flux should be continued, the profiles. Okay, so for example, you have, let's say, this, or maybe you have 2 different material. Okay, so this is material 1, and this is material 1, and this is material 2, let's say. Okay, and then you want to, so the temperature profile and the heat flux normal to the interface, so that this is the interface should be continuity. So maybe if this is the profile of the temperature, it would be maybe like that, like continuous, yeah. Okay, and then this is where it's also very important. The fourth one, at a solid fluid interface, the normal heat flux may be related to the difference of the solid surface to T0 and the bulk fluid temperature. Give me 1 second. Maybe I need to put the drawing. Wait, so this should be TO, yeah. There. Okay, so at solid and fluid interface, the normal flux component may be related to the difference between the solid surface temperature TO and the bulk fluid temperature of TB. So let's say, maybe I can give some example. For example, we have a ball or a sphere like that, yeah, and then this is the surface, and also the area for the bulk. Okay, so if this is a T at the surface temperature, TO, and this is the bulk temperature, TB. Okay, so the Q, the heat flux that the normal heat flux, so the heat flux over here, for example, let's say TB is higher than TO, the Q would be the H, or the convective coefficients, divided by multiply with TO minus TB. Okay, again, this is a driving force, and this is resistance. Okay, yeah, so this is we will of course we're gonna see this boundary condition a lot. We're gonna go back again to here to show, for example, if we get some examples. All right. Okay, so and then here Pak Anggit also has explained about the heat of conduction, yeah, similar to the Newton's law of viscosity. So I'm gonna skip it. So here you and again, if you're unsure about your equation, you can go back to the appendix B. Okay, in appendix B, in I don't know, B1 or B2, I think that would be all the formula for Fourier's law for the conduction for any coordinates. Okay, Cartesian coordinates, cylindrical coordinate, or spherical coordinates. Okay, you're gonna see that. All right. Okay, so and then the one that we're gonna see, the first one is conduction. In conduction, is actually usually between inside. It can be in solid, it can be fluid, but it is actually based on the molecular work. Okay, it is based on molecular work where the Q, for example, Qy, yeah, this one Q to the Y. Axis actually equal to minus K dt over dy. Okay, the K itself, the thermal conductivity, sometimes later on gonna be function of temperature, but in some cases we can make it as a constant, yeah, just to make sure that it is a constant, then we can apply it straightforward. But in some cases, if you're using like a very high range of temperature, the thermal conductivity would be a function of temperature. Okay. Right, and the second one, so this is the, I would say this is the one phenomena that you need to see about heat conduction. The second phenomena that you need to see is about convection. Okay, so convection is defined as there are two types of convection. The first one we call forced convection, and the second one is called the free convection. Okay, so in forced convection, just imagine we have a hot pipe, and then for example, I have this hot laptop, and then I add some fan to this laptop just to want to cool it down, the laptop, let's say. Okay, or here we have a hot pipe, and we have a fan, and the fan will force the atmosphere flow around the hot pipe there with some velocity, and then after that there would be some heat transfer from the hot pipe into the air. Okay, so usually the flow pattern are determined by external forces, which is this is going to be the external forces from the fan, and then it will cause some velocity around the air around the hot pipe. Okay, so first, how we gonna do that? The first one, we gonna find the velocity profile first. Okay, like I said before, velocity profiles, and then they are used to find the temperature profile. Okay, so it usually the usual procedure for fluid with constant properties. Okay, so and it is actually a Nusselt function of Reynolds and Prandtl. Okay, now let me check one by one. Do you know Nusselt? So I need to check I don't also don't remember all of them. So the from Nusselt number, all of them are dimensional number. Yeah, all of them is dimension number. So the Nusselt is actually this one. Let me write it here. So the Nusselt would be the h d over k, yeah, which is this one is the conduction, and h is the convection. So it is Nusselt number. So Nusselt number is actually hd over k. So it's actually the dimensionless number that compare the conduction parameters, the convection parameters, effective heat transfer divided by conduction heat transfer. Okay, if you have a system that has a very high velocity on that, then when you have maybe have a high convection heat transfer compared to the conductive heat transfer, so your Nusselt would be of course very high. Okay, but if you have a low convection heat transfer, and then it's compared with the conduction heat transfer, maybe you have a low Nusselt number. Okay, and then it's also a function of Reynolds. Yeah, do you remember what's Reynolds?
Rho du over viscosity,
Rho
Bu.
mu d over rho v
Rho
dv
dV,
ya?
rho dV
Oh
over
ya, rho dv
viscosity,
over
Bu.
mu. Rho v d over mu. This one is actually called from v multiplied with d divided by mu over rho. Actually, that actually the real function, yeah, the real function. And it is actually this is actually uh, the momentum transferred because of the flow, okay, divided by the momentum transferred because of the viscous. Okay, do you know what is this one? Mu divided by rho. It is called kinematic viscosity, yeah. Okay, so here's actually in Reynolds, you will see that if you have a high Reynolds number or in turbulent, so your momentum transfer is actually dominated by the flow, by the velocity of the convective or velocity of the flow. Okay, but if you have a low Reynolds number, like less than 2000 or maybe just 1 or 2 or 3, like where it is a very laminar flow, so your momentum transport is dominated by laminar flow. Okay, so this one Nusselt would be a function of Reynolds. So it is how convection and conduction heat transfer, the ratio of that one is going to be a function of Reynolds. I think if the Reynolds is higher, then convection is also higher as well. If the Reynolds is quite laminar, then the conduction would be in dominant. Okay, and the last one is Prandtl. Okay, anyone knows Prandtl? I think maybe in the what is called the wait need to check the formula. Forgot. Okay, so the Prandtl number here, so the Prandtl number is actually again also the diffusivity as well. Okay, so it's actually the Prandtl number would be the momentum diffusivity, which is kinematic viscosity is also called momentum diffusivity. Okay, diffusivitas momentum. It's actually mu divided by rho. Sorry. Mu divided by rho divided by thermal diffusivity, and then you're gonna learn later on that thermal diffusivity is actually called that K divided by C rho Cp. This is called thermal conductivity. That thermal diffusivity. I mean, okay. So here, and then after that, those rho will cancel out. So the Prandtl number actually would be mu Cp over K. Okay, so it is about diffusivity. This is about the the kinematic viscosity or the momentum diffusivity, and then divided by thermal diffusivity. Okay, so there you are. You see, so later on, that's why in chemical engineering we're gonna see a lot of empirical correlation, because that can show our phenomena. Is it dominantly caused by, for example, by the heat, the thermal, or about by the Prandtl, yeah, about the kinematic viscosity, or about the viscose, or about the thermal. Okay, so we can see that one. Okay, so later on we're gonna see some example about convection, the forced convection. The second one is the free convection. It is more complex, yeah, compared to the free convection. I would say I think we don't ask the free convection to be in the exam because it's very complex compared to forced convection. Usually in the exam, there would be always about forced convection examples, but the free convection is only for our understanding and or just all the concept. Okay, but for the how to derive it in the mathematically, and later on sometimes we need the numerical correlation. So but let's see, just make an example. Okay, and this one, the Nusselt it would be a function of Grashof and Prandtl number. So the Grashof number would be about, again, dimensionless. Okay, and then it is actually quite I think it's quite buoyancy force. So let me just copy some of them. So if I copy from the Wikipedia, you can see. Oh, I can see. Okay, you can see it in Wikipedia, but here the Grashof is quite. It actually. There's some equation here, but actually the Grashof number, it depends by the buoyancy force. Okay, so it's actually why there is a free convection. Let's say in the free convection you have a hot pipe and then you just leave it out hanging around on a cold surface. So so that means it's actually on a heated, or maybe for this case is the fluid is heated and then the pipe is not just pipe, a cold pipe. What happened is that there would be a buoyant force, kayak apa ya, gaya apung ya, a buoyant force, something like that, on the heated fluid, and then those forces, the buoyant force will have some velocity. Okay, jadi dia akan naik ke atas gitu ya. So the buoyant force has a velocity, and after that we can get some velocity profile around the pipe, and then later on we can see the temperature profile. Okay, so there it is. So there are three, like you learn in high school or in maybe university as well. You know there is a conduction, forced convection, and also there's a free convection. Okay, and of course there would be radiation as well, but it's not included in here. Okay, and this one is for you can apply convective flux, yeah, or convective heat flux like this. And then here you have the molecular work, similar as well. And then this is the energy production as well. Okay, so now we're gonna start some example. The first one about heat conduction. Okay, we don't need to like Pak Anggit said last week, we don't need to put all of this one out. Yeah, it is good if you want to write all of them, but then later on sometimes some of them would be cancel out. Okay, sebagian bisa dicoret. Okay, so here I would like to give you some examples about a heat conduction with some electrical heat source. Okay, so the key word of here one is we have a heat source or heat generation. Okay, so here if I can copy go back here, I can copy here. This is the shell energy balance, and then I copy maybe here. Maybe I can make it smaller. This one, okay, just one just to check the correlation with the mass balance, and also here. So here, the one that we're looking at, so we have a heat generation caused by electric sources. So we have a rate of energy production. So we have this one, okay, and then after that we don't and this one is actually electrical cable, okay, wires, or very long wires. Okay, so we have long wires, electrical wires, and then it's quite long, and then it's cylinder, and then it has some electrical conductivity inside this one, and then it has some current mengalir sebuah arus with some current density is I, okay, which is ampere divided by square centimeters, okay, or electrical flux. Okay, because of they flow like that, that would be some heat generation, or we call it electrical dissipation, which is SE equal to I squared divided by KA. So this is defined, yeah, this is defined from the problem. Okay, so if you look at, so if you want to write it from here, that's fine, of course, but if you look at here, so we don't have the convective transport, because we just only consider about the solid, yeah, we only consider about the solid. So then okay, so here the convective transport, it would be, we don't consider that one. Okay, and the work, also there's no work in here because only electrical sources. Okay, work done on the system, also no, we don't have the work because it's not about in the, it's not about in the fluid, yeah, it's only on the solid, so we don't do that. Okay, and then for molecular rate of molecular energy transport would be the heat flux later on. Okay, and then the heat flux here would be on the what we call the Fourier's law. Okay, so got it. So when you want to make the energy balance, you can start from this one here, but then this would be simplified with just the Fourier's laws and the rate energy production. Okay, so now is the assumption. The assumption first with the increasing temperature inside the wire is not too high, and the second one is the temperature on the surface of the wire is we assume to be constant at T0. Okay, so here is actually later on would be one hint of boundary condition. So, because it is cylinder, so of course we're gonna need to write about the coordinates here. So we can write the coordinate in the middle, and then this would be on the Z direction, and this would be on the R direction. Okay, once we know the boundary condition like this, so when we know that when R equal to the capital R, then T would be equal to T0, which is dijaga constant. Okay, so all of the on the surface, di semua permukaan would be T0. Okay, right. So again, so first we can start with energy balance. I think in here it is horizontal, but we make it vertical, maybe too easier to see, but that's fine, yeah. So here, so we consider about the heat production from electrical dissipation. Okay, so if we go back here from our energy balance, there is no energy convective transport because it's not a fluids. There is no work done on the system or by the system by molecular transport because it's not a fluid as well. There is no work done as well. So this would be the energy. Okay, there would be the energy in and out, and also the rate energy production, which is would be what we called here electrical dissipation. Yeah. So this is actually from electrical dissipation. Okay. Now, so here, so what you need to do first? Okay, the first one, like previously, like I said before, find the coordinate. So determine the coordinate. Okay, the second one, sketch the the system, and also the shell energy balance. Okay, so maybe we can start it from here. This is the coordinate, this is the R, and this is the Z, this is the Z. Okay, yeah, and after that we know that a shell balance similar to the circular pipe that you learned before. We have a delta R, okay, and then we have electrical dissipation and then also heat generation. Okay, so then the heat flux in would be the one that we see. Okay, if you in the momentum you thought about tau, okay, the momentum flux, or the Z, for example, but in here you write the Q or the heat flux. Okay, so this is the heat flux. Okay, so we can write that the and then it should be multiplied with the area again. Okay, the area normal to the heat flux. So we have 2VRL multiply with QR at R. Okay, and then it's this inside there, and then would be out that one. Okay, so then minus 2VRL multiply with QR divided by R at R plus delta R. Okay, and then plus with the heat generation laju produksi panas, ya, which is 2 VRL delta R multiply with SE, which is SE is the electrical dissipation, equal to I squared divided by KE. Okay, equal to 0. So this is going to be your energy balance. Okay, so here and after that we can see step by step, yeah, one by one. From here, for example, maybe from here we can see that the 2VL again. So again, similar with the cylindrical coordinate, the R in here is not equal with the R in here, so it can't be cancelled out. Okay, so we can't cancel out all of them because the R in here is actually revert to R equal to small r, while R in here equal to R plus delta R. Okay, so this is going to be different. Okay, so then we eliminate the 2V and L in this one here, so we can see that and then maybe just rearrange the equation, put the SE over there, and then make the minus become plus, something like that. So then we end up with RQR at R plus delta R minus RQR at R divided by delta R would be equal to RFE. Okay, so here again, similar with the previous one, I think you should be can be faster than previously. At limit delta R equal to 0, then you can get D of the RQR over DR equal to RFE. Okay, so with the integration, you can have the integration like this. It's just very similar with cylindrical tube case, yeah, right? So remember, if you have only like this, if you have boundary condition something like this, like C1 divided by R, always remember that this value is finite. Okay, so this one should not be in the equation. Jadi tidak boleh ada. So because this one's not, so that means C1 should be 0. Okay, so sorry, not this value, the equation, yeah. This the equation is finite. Okay, so this equation should be finite. So then C1 should be always 0. So in any case, okay, so if you find some cases where you have on the like this C1 equal to 0, you know that at R equal to 0, QR is finite. Okay, so at R equal to 0, the QR is not equal to infinity or should be finite, so then C1 should not be in the equation. Okay, so this would be equal to 0. Okay, so then the QR would be SER divided by 2, or the flux, heat flux would be increasing linearly with the R. Okay, so you can see that one. Okay, and then after that, then after that you can see that if you in the momentum transfer, you will see about the Newton's law. In heat flux, then you revert to Fourier's law. Okay, so this one is called the heat flux profile. Yeah, or okay, you can write the heat flux profile. If you want to know about the temperature profile, then you want to see the Fourier's law. Okay, so this one is the correlation. Oops, where is it? The correlation between heat flux and temperature. Okay, so this one again you have to you can start apply this one because it's a cylindrical tube, cylindrical coordinate. Then you should say QR. Okay, Q to the radius outside minus K dt over dr. Okay, and then you can substitute minus K dt over dr here to this equation, and then you get the integration. Okay, then you have the C2 over here, and remember about the boundary condition previously that we see here. Where is it? Yeah, this one we have the boundary condition. When R equal to the capital R, T would be equal to T0, right? So then you can apply it there, here, and then you see this one here. Okay, and then similar to the cylindrical tube case, rather than we see T equal to blah 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 plus T0 like this, we often see the temperature should be minus its reference. Okay, so in a heat transfer, usually we better to write the temperature as T minus T0. Okay, T minus T0 like this would be equal to this one. So at least we see the increasing temperature related to the references. Jadi kita lihat kenaikan temperaturnya. Okay, so this is the temperature distribution, or the temperature difference distribution. Lebih tepat kenaikan temperatur. Why? Because we always put the reference with T0. Okay, so it's much more convenient to do that. Okay, up to here. Any questions?
Bu,
Yeah.
Can you explain what SE is again, Bu?
Okay.
Sorry.
So SE is defined in the problem. It's called electrical dissipation. Okay, and it can be, so it is the energy that is generated because if you have wires, and then inside the wires there is electricity passing, and then it is defined as I square divided by KE. Okay, jadi seperti hilang-hilang panas, rugi-rugi panas. Yeah, it's like a loss, energy loss if you have this if you have electricity inside these wires. It is defined.
Then Bu, why isn't it included in like rate energy out gitu, Bu?
Okay. This actually why? Because they generate energy, okay? Because it's a rate energy. Wait. Okay, because this is the rate energy, so you have energy generated inside your wire, and of course it should pass ya. Ini kan harus meningkat ya. Harus apa? It has to be transferred. It should have the energy here should be transferred, and the energy will be transferred in the form of heat. Isn't it? So this one you have some energy. You have energy production. This one is called electrical dissipation, and this energy is actually should be transferred. Okay, and then it's transferred. It will drive the molecular transport the energy out by molecular transfer. So that's why it will affect the profile. So what happened is maybe so if I can draw the profile, or maybe it's better if I can open the birth book. Yeah, let's open the book. So if we can open the profile, is it in the profile there? Oh, okay. Oh, it's not in here. So yeah, so it's actually is it written in here? No, let's go back to the PPT then. So okay, so because of the heat generation here, then you will have this temperature difference. Okay, if I can draw just maybe let me try to draw it myself. If I have, let's say this is inside your wire, and then I make it bigger. Okay, and it's and this is, let's say, the middle. If you want to see the T minus T0, the highest generation would be on the inside. Okay, so when R equal to 0, that would be a maximum temperature. Okay, so when R equal to 0 would be a maximum temperature increase. Maybe I can draw it here. So when in the middle, because of the heat generation of the electrical dissipation, let's say on the R equal to 0, that would be a maximum of heat generation. Okay, when here would be about and when R equal to R, the T minus T0 equal to 0, so the T would be T0. Okay, however, when R equal to 0, that would be a highest increasing temperature, which is T0 plus SER squared divided by 4K. So your temperature profile inside the electrical wire would be about like that one, parabolic, yeah, because it's R square. It's gonna be very hot in the middle, but on the surface it will equal to the T0. Okay, so then would be a maximum temperature increase. Why the temperature is increased? That is because due to the heat generation from the this one, from the produksi panas per volume, yeah, this one. Okay, did you get it?
Yeah, kind of. But the thing that I'm still confused about is that like you have one source of heat, right, like which is the electrical wire. So why isn't the SE included in the rate of molecular transport?
No.
in or out? No.
Okay, the molecular transport only consider the conduction key. So uh, the molecular transport is actually is defined as Q. So this one is defined as Q or heat flux. Jadi dari flux panas. Okay, while the electrical diffusion, the source of energy we can consider of this one. Okay, yeah. It's just similar with what you call ya? Ada nggak ya energy generation? Maybe later on I can get some example in mass transport, but we haven't been that one yet. For example, in the mass transport, if there is a reaction, and then there would be a rate of reaction, for example, it will also would be in here. Okay, so that actually, so this one will be put into the rate of energy production. And later on, you're gonna see in here there are a number of we'll see. There are a number of energy production. Okay, it can be degradation of electrical energy into heat. Okay, that would be one case. Another one, if you have nuclear reaction. Okay, if you have a nuclear reaction in the fission process, it also will generate heat. Or maybe in chemical reaction, it also generates heat. And then all the viscous dissipation. If you have two fluids between two rotary equipment, kalau ada pelumas ya, and then you heat it up, and if you rotate the parts, sometimes the fluid become hot. It's because of the viscous dissipation. Okay, that's also the same. If, for example, using a fission process, that would be a nuclear process, for example, and it will generate heat, and the heat will be transferred in the form of conduction. Okay, this was also similar if the heat produced by the chemical reaction, for example, inside a fixed bed, and then the energy from the chemical reaction will be transferred, akan pindah ya, and then it will affect the temperature profile around the catalyst ball, for example, for the fixed bed. Okay, and that would be that term energy production. Okay, so the conduction only is actually this one, yeah. The conduction or the molecular work would be the impact of this one for this case. Okay, so the conduction would be the impact of the energy generation. Can you what do you think? Is it my answer can yeah, did you get some of them? What do you think?
Yeah, I guess it makes sense. If I may repeat ya, Bu. So, like for example, the electrical wire releases energy. So that is the total in SE, that one, right, Bu?
Yeah.
In 2 pi R L delta R, right? So that is in comparison to the difference in when it goes in R and it goes out in R delta R, right, Bu? Is it something like that, Bu?
Yeah. That's right. So would be similar to this one, yeah. So of course, if you because the thing is, if you only have let's say if you don't have electricity past your wire, yeah, of course there is no heat generation, right? So of course then there would be no Q. Okay, so if I can go back here, wait, if I can go back here, if let's say for some reason the electrical wire, I maybe just switch off the electricity and then wait for a while until there is no SE at all. Okay, so if the SE is 0, so that means there is no this one would be equal to 0, right? So there would be there's no Q, there would be no temperature distribution. The temperature would be similar, would be inside would be T0, outside would be T0 as well. Okay, but now because of the SE heat generation, the inside would be very hot, okay, or the maximum because of the heat generation. See, while the outside, yeah, the inside would be the maximum over here, yeah, because of the heat generation by the electricity, while the outside would be still 0. So because of there is a difference, then we can see the temperature distribution. Okay, so here again, and we also can determine the first one is the maximum temperature increase, yeah, this one, and then also the average temperature increase, like this. So the integral of the delta T are the theta divided by the cross section of the area, similar to the circular pipe. So it's around half of the maximum, the average temperature, and then of course the Q, the heat outflow at the surface, outer surface. Okay, so the Q would be the Q at R equal on the surface multiply with the area. Okay, it is similar with the shear force on the momentum. Maybe to sum up, I can open the book again, so we can see this is you can see on page 294, right? So okay, so here okay, so okay, so it's called that the reader, while going through this development, may be well aware that you had a feeling of deja vu. Okay, so there is, after all, a pronounced similarity between the heated wire problem and the viscous flow from a circular tube. So the notation is different. So the first, for example, the first integration in the tube flow will give tau or z function of r, while the heated wire you have heat flux, yeah, q r function of r. The second integration will give a velocity profile in the tube flow, while in the heated wire you have a temperature difference. Okay, T function of R minus the reference. Okay, and the boundary condition at R equal to 0, in here the momentum flux is finite, while in here the heat flux is finite. Okay, the boundary condition at R equal to capital R in the pipe, yeah, the circular tube flow, Vz equal to 0, while in here the difference of temperature, T minus T0 equal to 0. Okay, and then we can see the property, the transport property. For the heat transport, for the momentum transport, we use mu, viscosity, while for the heat flux we use K, or thermal conductivity. Okay, and then and again, so I think this can answer your question, yeah, Kevin, because the source term, so the source term that makes those the momentum flux is the difference in the pressure. Okay, P0 minus PL divided by L, while it is equal to Fe. Okay, and then the assumption when the mu is a constant, in this case the K and K is constant. Okay, so we can see that it would be quite analog process. Okay, all right, so I think this can add one more example to you, to the about the conduction, and on Friday we'll continue about examples in convection. Okay, all right, everyone, thank you very much for your attention, and keep healthy, and then I'm see you again on a Friday.